Hi, I'm Shravan. I'm a new assistant professor at UT Austin, and today I'll be telling you how to secure your applications from bugs in its dependencies. And so this is actually the result of a multi-year collaboration between a bunch of people at UC San Diego, UT Austin, and Mozilla. And today's talk, in a nutshell, is going to be about in-process sandboxing, which is this technique to secure your application from dependencies in the form of native code. And this idea of in-process sandboxing has actually been around in the academic security community for a while, almost 30 years at this point. And this is the first time it's making its way to production code. And this is because of a couple of reasons. The first is WebAssembly, which is this widely available toolchain for compiler-based isolation that is now available for all of us. And the second part is this framework we had to build called RLBox, which simplifies adoption of in-process sandboxing and lets you sandbox native code with WebAssembly. And the Firefox web browser has been using RLBox for over 2 years at this point. And this is something we believe other applications can do as well. So in this talk, I'll start with some high-level bits, like why we want something like in-process sandboxing in the first place. Next, I'll talk a little bit about the pain points, what the pain points of in-process sandboxing are, and why we need a framework to help us adopt it. We'll talk about RLBox, which is the framework we built to actually simplify in-process sandboxing. And finally, we'll talk about our experiences actually deploying in-process sandboxing with RLBox. So let's jump right in. The reason we care about any of this is that every application we use today in some way relies on native code. And as we probably well know, native code tends to have memory safety bugs. And if you've been to Black Hat before, you've probably seen a slide like this. This is basically an analysis of bugs in Google Chrome and Microsoft Windows. And what was found was 70% of all the bugs we see are just memory safety bugs. So use after freeze, buffer overflows, all of these things. And at this point, you might say something like, well, let's stop writing stuff in C++. I'll write everything in Rust, or something like that. And there's a problem there, which is these safe languages are also built on these same unsafe libraries. So if you look up the CC crate on Rust, or the add-on API in Node.js, you'll see this. And as just one other example, something like OpenSSL, 500,000 lines of C, it's a common dependency even in Rust applications, for examples. And the problem we have with all of this native code is when these libraries have bugs, they are used in real attacks. And we've seen this in the wild time and again, where these sort of bugs are exploited to compromise systems like web browsers, iMessage. You name a system, it's probably been compromised by something like this. And the challenge we're running up against is all of the techniques we have, the mitigations, the application hardening, like ASLR, stack canaries, control flow integrity, end up being just a little speed bump for in the wild attacks, something they have to get past, but eventually they do, and suddenly we see attacks in the wild. And we could try to say something like, well, let's rewrite everything in Rust. Unfortunately, this is not very practical. This is actually quite unrealistic. There are billions of lines of existing C and C++ code that aren't going away. And rewriting it is not just changing the syntax or something. You have to retest. You actually have to make sure it's portable, gets the same performance. It is quite a process. And to a point that even Mozilla, who developed Rust, is not really trying to rewrite all of Firefox and all of its dependencies in Rust. So instead, we have to look for something else to tackle these sort of problems. So one thing we can do is take all of this buggy native code and stick it into a separate process where it can't affect the rest of the application. This is the idea of process sandboxing, and it's been around for a while. It's convenient because all of our existing code works. That's great. But what we see is this technique is rarely used in practice, barring like a couple of exceptions, I think OpenSSH, web browsers. But other than that, it hasn't really seen widespread adoption. And there's a pretty good reason for this, and that is performance. When you have processes, you have inter-process communication. When you have inter-process communication, you have slowdowns in your application. There is a lot of overheads, CPU-wise, memory-wise, scheduler-wise, and there are challenges with scaling too. And even if you can get past some of these, What eventually happens when you use process sandboxing in your application is you are going to re-architect it. You're going to change the way it's written. It is hard to retrofit process sandboxing onto your existing application as is. Now, I could talk to you about this at great length, but instead, let me just point you to a great talk by Chris Palmer, who went from Google Chrome Security, who went through all of this in great detail. And instead, let me talk about a technique we tried that did end up working for us, and this is this idea of in-process sandboxing. So in-process sandboxing, it's a pretty simple idea again, which is we take these libraries that we don't trust, we compile them with WebAssembly to sandbox them, and then we run them in the same process. And for the purpose of this talk, it's sufficient to think of WebAssembly as this compiler that can isolate code using runtime checks. And what we're trying to get when we do all of this is to make your application look something like that. Not this big monolith blob of code that can access any part of the address space, but something with clear components which are sandboxed. And the sandboxed components can only access a portion of the address space. So for example, there, libjpeg can only access addresses between OX4100 and OX4200. And the end result of doing something like this is when you have a user after free, a buffer overflow, or something similar in libjpeg, it does not touch any of the memory of the main Firefox process or any other component. And this is really nice, because we now get code reuse, and we also get performance. There is no processes, hence there is no IPC. CPU overheads are great. But we still have this open challenge now, which is the engineering effort involved. We still have to take this idea of in-process sandboxing and put it into our existing million-line code base and so on. And it turns out this is a really hard problem, at least to do by hand. You do need some help. So let's talk about that. Let's talk about this, what the pain points of in-process sandboxing are, and why we need a framework to help us adopt this in the first place. And the best way to kind of get a sense of what's happening here is with an example. So we're going to use this as our running case study. We're going to try to sandbox libjpeg in the Firefox web browser. Again, the goal is isolate libjpeg. Any memory safety errors in libjpeg do not affect the rest of Firefox. So step one here, really simple. Take libjpeg sources, run it through the WASM compiler, produce a sandboxed libjpeg binary. And under the covers, WebAssembly is adding range checks. So the way it actually ensures sandboxing is with range checks like this, where any memory read you have in your application is just transformed to a range check, followed by the same memory read. And it's a pretty simple idea, and I should point out that in practice, there are a bunch of tricks involved to make these sort of range checks, like to optimize away these range checks for performance. But this should give you the intuition. And broadly, we know how to do this. This is, in some sense, the simple bit. The really difficult bit is we now need to modify Firefox to incorporate this sandbox libjpeg. And this is the bit I want to focus on for now. And let me actually walk you through the various steps now that are needed to incorporate this modified libjpeg. And the first thing we would do, if we wanted to do this, is decouple the library. And this is not just a matter of like grabbing the code and putting it in a separate folder. No, we need to grab all of the shared data structures. We need to figure out how to disentangle the shared control flow. All of these things have to be carefully separated so that we can actually sandbox libjpeg correctly. And once we do this, we need to now go back and think about all of the data sharing that needs to happen. Because components now have their own separate memories, so we need to marshal data back and forth between different components. And this is actually made challenging by a couple of different factors. The first one is WebAssembly is a different compiler. It has a different ABI. It has different calling conventions. Some of these are chosen for performance reasons, but they are different from the rest of Firefox. So we now need to deal with this. We have to have a patchwork of code that fixes all of these things before and after every time we marshal data. And the second bit is we can't just stick this marshaling code wherever we want. We need to do this very carefully. We need to do this lazily so that we limit the amount of marshaling and limit the overhead of marshaling data back and forth. And once we complete all of this, we still have to think more about security. Because when we started, libjpeg was a trusted library. Firefox trusted libjpeg, and it trusted libjpeg's outputs. What we've said now is libjpeg is sandbox. We don't trust it. We shouldn't trust its outputs. Meaning we now have to go back to the Firefox code, find all the places libjpeg's output has been used, and add some sort of sanity check or data sanitization there. And making all these code changes gets really difficult. And the best way to see this is probably with an example. So let's look at some code. So that's a very simple 10-line example of an application that renders images with libjpeg. You don't have to read all of that in great detail. I think the broad thing to keep in mind there is there's an application that renders images. There are a couple of calls to libjpeg APIs. And we want to modify this application to do all of the things we just talked about: marshalling, ABI fixing, security checks. So if we actually went ahead and did all of those changes, the resulting code is going to look something like this. Nearly every line of that code of code has changed. And it is, and if you actually read what's there, which I do not recommend, you're going to see that it's almost impossible to understand. And here's the best bit. If you get any of that wrong, your security is completely compromised. Like, all of that sandboxing counts for nothing. So this is where we found the practical challenges lie, and we really had a hard time doing this by hand. And we basically came to the conclusion that if we have to write code like this, it really falls flat in practice. So even that 10-line example was difficult to look at. Imagine doing that for a real code base with tens of thousands of lines of code for an image renderer. The diffs are going to be insane. And kind of the core problem here is code like that exposes details of the sandboxing in your feature code. And what we've done is we've mixed up security and feature work. And it really becomes unclear who even should maintain this code at this point. Is it the security team? Is it the feature team? What happens if you want to update something? Who has to review it? And if you want to add more features to that code, testing, debugging, good luck. And even better, we've ported that for one ABI. Presumably, we want to support Windows, Linux, a couple of platforms at least. Repeat that one more time, 2 more times, 3 more times. And if you somehow miraculously do all of this, repeat that for each library you now want to isolate and sandbox in this way. And we basically, so we came to the conclusion we can't do this by hand, and we weren't even alone in this. So people at Google also tried this and came to pretty much the same conclusion as we did. This is really hard to do by hand. So to address this problem, we built the RLBox sandboxing framework. So RLBox is this framework that's meant to simplify adoption of sandboxing into your existing large code base. And the core idea here is to use types. We use types to hide all the low-level details. So ABI, data marshalling, all of this stuff is automatically handled. We use types to track untrusted data and control flow. So if you're missing security checks, you will get a compile error, which is really nice. And we use types to even let you identify and make changes to code incrementally, line by line, and you can even pause and test your application. And the really cool bit of all this is RLBox is a pure C++ library. So you can drop it into your application without changing your compiler, build systems, any of that stuff. It should just work. And at a high level, RLBox is pretty simple. There are just 3 principles. The first is control flow should be explicit. So if you make a function call to a API, to a library like libjpeg, which you want to sandbox, you have to go through this API called sandbox.invoke. The second is RLBox forces any data coming out of the sandbox to be marked as tainted. So if you access the size of the JPEG image, which is output by libjpeg, you're not going to get a U32. You're going to get a tainted U32. Oh, and I should point out, if you mess up in making any of these changes, RLBox will force a compile error. So you have to get this right. There's no way to get this wrong. And finally, once you've done this, the third principle is you need to make sure all tainted data is checked before use. So if you now take this previous size, which is tainted, and stick it into a memcopy operation, you're going to get a compile error. The way to fix that is to call this API called copy and verify. And what that gives you a chance to do is sanitize this data. And once you do that, the tainting is removed, and that will compile. And Again, let's go back to that same example and apply these 3 principles. Our goal is to migrate the code in the same way that we did before, except this time with RLBox and these 3 principles. And I'm going to start with just the first 2 there. If I were to make the changes for those first 2 principles, which is sandbox.invoke and tainted data, the code is going to look like this. And even without reading it, hopefully you can see right away that it's a little bit cleaner. It's a little bit easier to read. And all of this is because RLBox is automating a lot of things behind the scenes. All of that ABI craft, all of the data marshalling, that goes away. It's even able to automate some of the required bounce checks that you need to have. So in that example there, you actually need a bounce check because you are dereferencing a pointer that libjpeg has given you. So there's a security check involved usually when you have to do that. And so now that we're done with these first 2 principles, let's focus in on the 3rd bit, which is tainted data must be checked. So if we look at that principle, we'll see that this variable size at the bottom is tainted. And the reason it's tainted is it's computing the number of pixels the image would have based on JPEG image metadata, which itself comes from libjpeg. So it makes sense. It should be tainted. And size is being used, again, in a memcopy later on. So we need to validate it. And to get all of this to compile, we should validate this and remove the tainting. And we can, in this case, if we stare at this code a little bit, we can identify what sort of security check we want. The main thing we want to make sure is that when we copy data out, we don't go past the end of the output buffer. So let's add that security check. We call copy and verify. Make sure that the value of size is less than the output buffer size. And then we use this checked value in the memcopy operation. And at this point, everything should compile. And this is really what RLBox brings to the table. It brings some sort of closure to this process of modifying code. Because if you compile this code, and if you're successfully able to compile this code, this is RLBox's way of telling you you're done with sandboxing. This should work. And in effect, the takeaway here is when we use WebAssembly and RLBox, we get the 2 things we're looking for, which is fast sandboxing and low engineering effort. And to really give you a sense of what this looks like in practice, I'm just going to very, very briefly tell you about our experiences deploying in-process sandboxing using RLBox. So the first thing we did, and the first thing we should always do when developing a new framework, is try it out. So we tested a whole bunch of applications to sandbox several libraries. So applications like Firefox, Node.js, Apache, and so on. And we sandboxed several different classes of libraries. Image and font rendering, audio-video playback, XML parsing, there's a whole list. And broadly, what we saw is that RLBox is able to automate away hundreds of lines of glue code to do with all of the same ABI, marshalling, and even security checks. And what's left for us is pretty much like what you saw, a few pieces of tainted data that we need to validate, typically at most 2 to 4 lines of code for this validation. And what this lets us do is sandbox a library in any one of these applications in just a matter of a few days, with a confidence that we've actually gotten it right. And at this point, we actually turned towards deployment. We wanted to make this production and deployment ready. So we worked for a while, and in February 2020, we actually did this. We actually managed to ship RLBox in the Firefox web browser. And we started really small, sandboxing just one library on just a couple of platforms, just Mac and just Linux. And over the course of like 2 years since then, we've been working on improving performance, portability, debugging, a whole bunch of things. And as of this year, we've actually sandboxed a handful of libraries across all platforms that Firefox supports. And this includes Android as well. And from the performance side, we also wanted to make sure that our sandboxing didn't introduce very large overheads. So we measured a couple of the high-value use cases in Firefox. So we measured XML parsing, sandboxing XML parsing, and font decompression. And broadly, we see that that's around 10%. And this allows us to make a security versus performance trade-off that's sensible for our application. For a browser, these two are just one of the billion things that a browser does. So 10% on one of the billion things is not something that's perceivable by the end user. So we are actually OK with this. So this works really well, and we actually did deploy all of this. And we aren't done. We are working on a whole bunch of things, improving several things. On the performance side, we are still waiting on things like threading to be fully standardized on WebAssembly. And we're trying to keep on top of adopting these things into the library sandboxing world as well, so that when we sandbox libraries that need these features, they work as expected. We've also done a ton of work contributing back to sandboxing toolchains to make sure they work well on low-resource environments. So 32-bit architectures like Intel 32, ARM 32, and so on. And one of the challenges there, which we've made some progress on, but we're still addressing, is it's not just the memory footprint. It is the virtual memory footprint. Virtual memory is also a premium in platforms with 32-bit pointers. So we are doing some work trying to improve all of that as well. And finally, on the usability space, we're also revamping the RLBox API. We're trying to make it conform with all of the modern C++ idioms as they evolve. And there's a bunch of work we're doing on the space to make it easier to use as well. And so if all of that looks interesting to you, try it out. Help us get this right. Use it in your application, and let us know what worked, what didn't. And if you're more on the attack side of things, let me point out that RLBox is actually covered under Firefox's bug bounty. And it's covered as like a sandboxing bug bounty, which means you get to start by adding a memory corruption into your favorite library that's sandboxed. And if you can escape the sandbox, you get the bug bounty. So let me briefly conclude by saying in-process sandboxing is this technique. It's a practical technique to secure the native code in your application. It is an idea that's been around for 30 years, and it's seeing production for the first time because we now have the tools to deploy this and use this. RLBox is the framework we built to actually use in-process sandboxing and simplify the adoption of in-process sandboxing into your application. And RLBox is a production-ready tool. It's being used by Firefox. It's been used for the last 2 years. And this is hopefully something you can use in your applications as well. So thank you, everyone, for your attention.